Okay. Welcome back, everybody, from lunch to the last, but certainly not least, session. And this will be on lattice problems and their complexity. And our first talk is reductions from module lattices to free module lattices and application to dequantizing module LLL. The work is by Gabriele De Micheli, Daniele Michancio, Alice Pellet-Marie, and Dan Nam Tran. And Gabriele will give the talk.
Great. Thank you for the introduction. So, well, as Chris just said, I'm going to be talking about reductions from module lattices to a special type of module lattices, which are free module lattices, and also a main application and also motivation for this work, which was to dequantize the algorithm module LLL. So unfortunately, Nam was supposed to give this talk. He's not here due to visa issues, so I'll try my best to give a talk. So let me start with the main motivation and the main result of our work. So we focus on algebraically structured lattices, and these are main candidates for lattice-based protocols that have been standardized. Actually, today, I think the PDF for the standard came out in the NIST post-quantum competition. And we really like them because the algebraic added structure to these lattices are often exploited for efficiency reasons, for example. So in our work, we focused in particular on what is called a module lattice, which I will define later. And we asked the following question. So if we restrict these module lattices to a particular type of module lattices with additional structure, in our case, this specific additional structure that we're adding over module lattices is this notion of free modules that I will define. Well, does this restriction make standard algorithmic problems that we often deal with in lattice-based cryptography, so SVP, CVP, or related problems, easier? So that's kind of a question that have come out very often in lattice-based cryptography. We're adding algebra, we are adding structure to an object. Are we actually weakening the security of schemes or not? So we focused on this question, and actually, I'm going to give you the answer right away. The answer is no. So in our work, we show that free modules are actually no weaker than arbitrary modules. And so for kind of standard algorithmic problems, so namely SVP, CVP, and a variant of SVP, we show there exists a probabilistic polynomial time reduction from the module version of this problem. So far, P is just for problem in general, to the free module version of this problem. And so this reduction is the main topic of this presentation, and its application I will discuss at the very end. So I will try to keep it very mathematically light, but I still need to introduce some objects that we'll need to understand what is going on. So a module is an algebraic object, and it lives in something which is known as a number field, which I'm sure many of you are familiar with. For those not, just think of the number field as a quotient ring. We have a ring of polynomials with rational coefficient, quotiented by a polynomial, an irreducible polynomial of some degree d, and d then is referred to as the degree of the number field. In a number field, we have something called the ring of integers. And at this point, I think if you're not familiar with these objects, just think as k as q, the rationals, and its ring of integers as d, just the rationals. Now, more concretely, what is going to be a module? So a module is going to be a subset of this number field k to the m, which is going to be finitely generated by a set of vectors. So here, VIV up to the VT, which are elements of these of this number field k to the m. So m copies of the number field. Now, if you set m equal to 1 in this definition of a module, you go back to an ideal, a fractional ideal. So think of a module as kind of a generalization of an ideal. Now, these vectors that generate our module are not necessarily linearly independent. And so for modules, we will often talk about this notion of a pseudo basis for a module, which is not a basis, in the sense that we will define the module with a set of k, this time linearly independent vectors of our number field, and also a certain number of ideals. And these tuples, ideals I and vector bi, up to n, where n would be the rank of the module, is known as the pseudo basis of n. Now, there's a particular case where all the ideals in this definition of a pseudo basis are trivial ideals, so they correspond to OK. And in this case, we say that the module is free. So we have a free module, and so in simple terms, a free module is going to be a module which has a basis. as opposed to more general modules, will only have the notion of a pseudobasis. So for cryptographic purposes, we often care about geometrical notions. And so as described so far, we have this module as an algebraic object, and we would like to see modules also with some geometrical properties. And one way to add some geometry to modules is to consider embeddings that exist from K, from the number field K, to the complex C. So in particular, for a degree D number field, we're going to have D embeddings. And one way to embed the number field into C to the D or R to the D is by using what is known as the canonical embedding, where an element X of the number field K, so a polynomial X of some degree D, is mapped to sigma 1 of X, sigma R of X, et cetera, where these are all the evaluation of the polynomial X into the complex roots of the polynomial that define the number field. So I believe I called it D in the definition of the number field. And this allows us to induce some geometry over K. And for example, we can talk about some notions like the shortness of an element of K, for example, by referring to it as the shortness, for example, of the vector sigma of X. This is a way of having geometrical properties expressed in an easier way. And embedding our module M to R to the Dn is going to give a rank Dn lattice in the sense of a lattice, Euclidean lattice, as we know. Now, as I mentioned in the very beginning, we will focus on a set of standard algorithmic problems that are often considered in lattice-based cryptography. Those are standard problems which the definition I'm just going to recall here. We focus on SVP, the shortest vector problem, where given a lattice or a module lattice, we're asked to find the shortest vector in this lattice, non-zero, of course. We have the closest vector problem, similar statement. We're giving a lattice or a module lattice. We're giving a target point, which is not a point in the lattice. And we're asked to find the lattice point, which is closest to this target element. Now, often in cryptography, we care about approximate versions of these problems, not necessarily the exact version. So we have gamma SVP, gamma CVP, where we relax the condition on the solution to be the closest or the shortest up to an approximation factor gamma. And in our work, we also consider the Hermit SVP variant, where the upper bound on the norm is not linked to the first successive minima, but this time with the volume of the lattice. So these are the main problems we will focus on. So now going back to the contribution of this work. So we show that for a problem P, and in this case, P is going to be either CVP, SVP, or HSVP for the Hermit variant of SVP. There exists a probabilistic polynomial time reduction from the module version of this problem for a module of rank n to the free module version variant of this problem for the same rank n. So because the techniques are actually quite similar for the three problems that we look at, I am just going to focus on SVP so far. So the P, which standard for problem, is going to be replaced by SVP. There are some technicality, some small technical details that change for the analysis of these reductions, but they mostly follow the same structure. So focusing on SVP, and I will leave you to the paper for these slight differences. Now, in order to show this reduction, to see how the reductions goes, we divide it into three sub-reductions, which I will now present. And as I mentioned in the beginning, I will kind of conclude the talk by the main application and also main motivation of this work, which was to provide a fully classical algorithm, LLL algorithm for module lattices. So let me start by the general layout of how these reduction work. So we start with the module version of SVP for a module of rank n. And our first step is to show that this problem reduces to free module SVP, again for rank n, and ideal HSVP, so having an oracle for ideal HSVP. Our second step will be to show that ideal HSVP reduces to a free module SVP, but this time for a free module of rank 2. And the third step is going to be free module SVP for a free module of rank 2 reduces to free module SVP for a free module of rank n. And now combining these three reductions together, we have the main reduction that we want to show in our paper, which is from module SVP to free module SVP for the same rank. So now I'm going to look at all these three sub-reductions one after the other and kind of give a general idea of how these reductions work. So step one, this was the first of the steps. So the goal is to find a reduction from modulo SVP to free modulo SVP and ideal HSVP. Now, the main technical tool that we'll be using for these subreductions, there's going to be one tool per reduction, it's very convenient, is this notion of almost free representation of our input module. So what is an almost free representation? If you recall, a pseudo basis of a module had tuples with an ideal and a vector, and my module was free if all of these ideals were equal to OK, to the ring of integers. Now, in an almost free representation, like the name very clearly states, we almost have a free representation, except we have one non-trivial ideal, in this case, the last one. And such a representation can be computed in polynomial time. Just believe me on that. There's results that show that we have polynomial time algorithms to find such a representation. So how does the reduction works now? So as an input to my reduction, I have a rank n module n. I have an oracle for ideal HSVP, I have an oracle for free module SVP, and I want to output a solution to SVP for my module n. The structure of this first reduction is actually quite simple. The only computation, the only thing I have to do is step one, which is not calling an oracle. So I compute an almost free basis of m of my input module, and as I literally just said, this can be done in polynomial time. Now I have my almost free representation, so I have my vectors vi, and I have one tuple with a non-trivial ideal I. I have an oracle for ideal HSVP, which I can use to find a short element of my only non-trivial ideal I. And so I find a short element alpha of I, non-zero short element. Now, using this element alpha that I just found, I can construct a free submodule of M, which is going to be spanned by the following basis. So the vectors b1 to bn minus 1 are the same as for my module M. And the last vector bn, I multiply by my short element alpha. Now, this is shown in the paper that it is indeed a submodule of M, and that we have a free submodule of n. We have a basis for it. And solving free module SVP with this free input n actually gives me a solution to SVP in the initial module M. So this is my first reduction. I have now a solution to SVP for my module M, which was not free. Now, let me move to the second step. So now the goal is to find a reduction from ideal HSVP to free module SVP, this time in rank 2. So as I said before, we have one tool per reduction. And in this reduction, we will exploit this notion of two-element representation for the input ideal. And so the theorem informally stated here that we're going to exploit is the fact that every ideal I in a number field can be expressed using as the sum of two principal ideals. So this two-element representation, meaning that we have these two generators A and B, again, that they can be found in polynomial time, which we can use to express our ideal I. Now, how can this be used in our second reduction? So as an input, I have an ideal I, and I have an oracle for free module SVP in rank 2. And I want to output a solution to ideal HSVP for my ideal I. So the first thing that I do is that I'm going to transform my input ideal into a free rank 2 module. So how do I do this? Well, I use this two-element representation. So I find these A and B, my two generators for the principal ideals, and I construct M2, a free module of rank 2, which has the following basis. So it uses A and B, and then an epsilon value, which has to be properly defined for the reduction to work. Now, I have a free module of rank 2. I can use my oracle to find a solution to SVP with input this M2 vector, M2 module, sorry. And the solution should be of the form some combination of A and B. So the first element of the solution to SVP is an element of my ideal I, and some second coordinate, which depends on this epsilon value. Now, the quantity UA plus VB can be shown that is a solution to ideal HSVP in my input ideal I. And again, for this to work, the epsilon value here is quite important in the sense that it has to be properly upper bounded and lower bounded. We want to avoid the case, for example, where the first quantity is equal to 0, and it has to be obviously sufficiently small for to be a solution to ideal HSVP. But I'll refer to the paper for the technical details of appropriately choosing this epsilon value. But in the end of the reduction, we do have a solution to ideal HSVP for my input ideal I. And now let me move to my third reduction. So the third reduction is kind of the most trivial one. We want to find a reduction from free module SVP in rank 2 to free module SVP in rank N. And here the idea is, the reason why I said this reduction was the most trivial one is that we all interestingly have this idea that these problems become harder and harder as the rank increases. So the main technique here, the main tool that we use, which is not a theorem like for the previous two reduction, is the fact that we embed the rank 2 input module into a larger module, and we kind of pad all the extra dimensions, so the n-2 dimension with dummy vectors, again, with appropriately chosen parameters. So more precisely, what happens in this third reduction? So we have a rank 2 module M2 for which we have a basis. Here I call it B tilde. And I have an oracle for free module SVP in rank N, and I want a solution to free module SVP in rank 2. So I construct this rank N free module M, which is generated by the following block matrix that we have here. So on the upper left quadrant, I have this B tilde basis, so my basis for M2. And then as I just said, in the lower right quadrant, we pad the extra dimension with these dummy vectors, which is the identity times this delta value. And again, this works if the delta value is appropriately chosen and upper bounds are provided in the paper. Now, using the oracle, I can solve SVP on my free module M, and I obtain a solution. And then we show again in our paper that the truncated version of this solution, so the first two coordinates of this vector S tilde, of the vector S, which we call S tilde, is a solution to free module SVP for the rank 2 module. And again, I emphasize here delta and epsilon are two rational numbers that we add in the constructions of these modules, which should be appropriately chosen. So let me kind of summarize these three reductions that I just mentioned. So we started with a module SVP with a module of rank N, and the end goal is to show that this problem reduces to free module SVP with the same rank. Our first step was to show that it reduces to free module SVP for a rank N free module with an oracle for ideal HSVP. And in this first reduction, we exploited the fact that we have this almost free representation of an input module, which can be found in polynomial time. The second step, we showed a reduction from ideal HSVP to free module SVP for modules of rank 2. And the main tool that we used in this case was this two-element representation. And finally, we had this kind of trivial reduction from a rank 2 free module to a rank N free module, where we just kind of added some extra dimensions and showed that we had a solution for SVP in the bigger module. And combining everything together, we show the main result of our paper. So this is the formal statement of our theorem. So basically, it repeats what I just said, except more formally and with the appropriate approximation factor that we have from the initial problem to the second problem, for which we have a loss, of course, but a controlled loss. There are two main takeaway messages that we have from this reduction. The first one is the initial statement that free modules are no weaker than arbitrary modules for standard cryptographic problems, and in particular, we focused on SVP, HSVP, and CVP. So this was the main takeaway. There are no vulnerabilities or that can be introduced in a protocol if we focus on a specific structure, in our case, in focusing on free modules. The other bullet point, which is not really a takeaway message, it's more like an observation, is that the framework of these reduction is quite flexible. And so we focused on three problems. We could consider reductions for other commonly considered algorithmic problems. We just haven't really looked at those. And I have no idea how much time I have left. Yeah, I'm good. Okay. I think I'm talking a bit fast, but so the kind of last point that I would like to mention in this talk is one of the applications of this reduction, and also kind of the main motivations of why we focused on these free modules to start with. So the idea was to dequantize module LLL. So I think you've all heard quite a bit about LLL during this crypto conference. Module LLL, the idea of module LLL is to have an extension of this LLL algorithm, except this time where the input would be a module lattice. Now, we have, since 2019, a quantum algorithm for module LLL by Ali, Pellemari, Chelet, and Wallet, where in their paper, they provide a heuristic quantum algorithm, which works for any number field, where you take as an input module lattice, and as an output, you have, similarly to LLL, you have a reduced pseudo basis for your input module. Their algorithm is extremely nice, has a few barriers to being practical. One of them was the fact that it was quantum, relied on some quantum computations. The second one is that the polynomial time depends on oracle call to the CVP problem in a fixed lattice that depends only on the ring of integers. Now, they also noted in their algorithm, in their paper, sorry, that their algorithm would be classical if the input module was free. And so the main motivation was this work initially was to dequantize this module LLL algorithm, so to remove one of the two barriers that would bring this algorithm to implementation ready stage. And these reductions presented in this paper show that actually we do have a classical algorithm for the module LLL algorithm. There's also other ways to dequantize the algorithm, but using similar techniques that appear in these reductions. And so that was kind of our initial motivation. Now, one could wonder if we do have a module LLL for module lattices. Well, the answer is still no, because we have this oracle call that still remains, which is a tough open question in the area and would be interesting to solve, but prevents us from having a real algorithm, I want to say. And with this, I'll finish here. Thank you so much.
We have a couple of minutes for questions. Yeah. I have one question. Could you go back to the formal theorem statement?
Yes, if I know how to go back, I will. But apparently, it's the small red button. Yeah, that's what I'm pressing. Oh, okay. It's just yes.
Yeah, so I was wondering. Sorry, I was wondering about the approximation factor. It looks like if the oracles provide a gamma approximation, then the reductions provide roughly a gamma cube. There's no dependence on the overall rank of the modules, though. Is that
no?
Right?
There's no dependence. There's dependence on the oracles, on the discriminant of the number field. So
Right.
delta k I haven't defined as the discriminant, and on the degree of the number field, but we don't have any dependence on the rank of the module rank. Also, I just to like continue on the answer, these upper lower bounds are not necessarily tight. We believe that there could be ways to combine our reductions in a better way to have tighter bounds.
And the module LLL kind of gave the feeling that somehow rank 2 modules are enough to handle larger modules as well. So this work is sort of pointing in the direction of rank 2 being the rank that's both necessary and sufficient for hardness.
Yeah, exactly.
Like
yeah.
Okay. How do we get it? There's a question on chat. There we are. Okay. Thanks for the nice talk. The strategy you described doesn't apply to n equals 1. Is it known whether principal ideal SVP is as hard as ideal SVP for arbitrary ideals? Can't use the mic because it's late at night here. Okay.
Yes, so this all applies for n greater or equal to 2. I think that's not the question. Is it known whether principal ideal SVP is as hard as ideal SVP for arbitrary ideals? I want to say yes, it is known. It was proven a few years ago. I know there's some experts in the room that can answer. Thomas, where are you? But I think the answer is yes. It is known. It is principal ideal SVP is as hard as ideal SVP for arbitrary ideals. He's not here, so he can't confirm, but I think it is yes.
All right. All right, so that's our time. Thank you, Gabrielle, again. And our next talk is, while they get set up, a lower bound for proving hardness of learning with rounding with a polynomial modulus by Parker Newton and Silas Richardson. And Parker will be giving the talk. And here comes Parker. All right, the floor is yours.
Cool. All right, everyone can hear me all right. So good afternoon. I'm Parker Newton, and today I'm going to present our work entitled A Lower Bound for Proving the Hardness of Learning with Rounding with Polynomial Modulus. This is a joint work with Silas Richardson from UC Riverside. So learning with errors is a computational lattice problem. It's a fundamental hardness assumption in modern cryptography. It can essentially be viewed as the problem of solving a noisy random linear system where each of the linear equations is perturbed by an error term from a probabilistic distribution. And it's been shown in prior work that LWR is at least as hard on average as worst case lattice problems. And over the last almost 20 years or so, we've been able to construct a plethora of cryptography from LWR. The problem has a few parameters, namely a modulus q, a dimension n, and an error distribution chi on z sub q. So it can be modeled, the problem can be modeled via challenger-adversary game. So the challenger chooses a secret vector, and the adversary can make a polynomial number of queries of the challenger. In each query, the challenger outputs a pair AI BI, where AI is a random vector, and BI is the inner product of AI with the secret vector with an error term from the distribution chi. At the end of the day, the adversary has to submit a candidate secret vector S prime, and we say it wins if it guesses correctly. So over the years, we've been able to construct a whole bunch of cryptography from LWR, but one sort of general class of cryptosystems that evaded us for a while were these deterministic cryptosystems. So a question that was asked is, can we construct PRFs directly from LWR? And it turns out not exactly, but in 2012, Banerjee, Peikert, and Rosen introduced the problem of learning with rounding, which is a de-randomized version of LWR with deterministic error generation. It's parameterized by a few parameters again, a modulus q and a second modulus p, which is less than q. And there's this rounding function, which maps each element of zq down to the nearest integer mod p. So here I've drawn the number line zq, and for the example where p is 2, if you work this out, you could see that roughly half the elements round to 1 and the others round to 0. So the problem of LWR is going to use this rounding function in order to deterministically introduce error into linear systems. So the game is almost exactly the same as LWR. The only difference is that in each of the pairs AI BI, BI is just equal to the rounding of AI with the secret vector S. But besides that, the game is exactly the same. And so in BPR12, they constructed PRFs directly from LWR. And all that remains to analyze is, what can be said about the hardness of LWR. And so indeed, the authors prove that LWR reduces to LWR when the modulus q is superpolynomial in N. And how the reduction goes is through this type of reduction that we call the rounding reduction, where on the right-hand side, we have a solver for LWR. On the left-hand side, we have a challenger in the LWR game. And the reduction algorithm is going to transform these LWR input points into LWR points by just rounding off the error in each of the BI elements. And so, the hope is that if each of these AI BIs is distributed from LWS, then each of the transformed AI prime BI prime elements is distributed from LWRS. If this is true, then the solver for LWR will just recover the LWR secret vector, which is the solution to the LWR problem. And so this works when Q over P is greater than is going to be much greater than N. And you can think of intuitively, why this is because, there are these dangerous points that lie really close to these rounding boundaries. And so you don't want to land on one of those points. And so you can show that with good probability that won't happen when this is true. Originally, this was you can satisfy this with Q being super polynomial, or as in subsequent work did with polynomial Q, but however incurring a priori upper bound on the number of input samples to the reduction. So, these parameter regimes are all suboptimal for various reasons. Large Q impacts the performance of LWR-based cryptosystems, where bounded M restricts certain applications. And so what we ask is, does LWR reduce to LWR for polynomial Q and general polynomial M? And what we showed is, in this setting, if chi is any LWR error distribution, then assuming the hardness of LWR, the original rounding reduction won't work. More generally, you actually can't reduce LW to LWR in a generalized notion of this that we call a non-aborting pointwise manner. I'll explain a little bit more about what that is in a second, but intuitively, we say that a reduction works pointwise if each of the LW input points is mapped independently to an LWR output point. And by non-aborting, we mean that you have to use all the samples. You can't reject any of the input samples. And so consequently, this establishes a lower bound for proving the hardness of LWR from LWE, because any reduction in this setting either can operate pointwise or must do some sort of rejection sampling. So now I'm going to explain a little more precisely about our model of a pointwise reduction. But first, let's take a step back and let's think about how a general reduction from LWE to LWR should work. So on the right-hand side, we have a solver for LWR. On the left-hand side, a challenger in the LWE game. And we're going to think about how the reduction should work. And so there are two rules that we want to establish right off the bat. First is that the reduction algorithm should work efficiently. It should be an efficient process. And the second is that whenever the person on the right-hand side, the solver for LWR, solves LWR, then the reduction algorithm should be able to solve LWE. So in a little more detail, the reduction algorithm gets a polynomial m number of input points, and it should transform those into some m prime number of points which are input to the solver for LWR. Solver for LWR outputs a vector s prime, and the reduction algorithm should be able to use that to efficiently recover the LWE secret vector. And so in a pointwise reduction, we're going to follow that template, but add a little more structure to it. So the first little modification that we're going to make is that each of the input samples should be mapped independently to an output sample following by an efficient function f. And secondly, you have to use you can't reject any of the samples. You have to use all of the samples. So this is what we mean by a non-aborting pointwise reduction. But going forward, I'm just going to, for simplicity, call this a pointwise reduction. So what we show is that under our parameter assumption, there does not exist a pointwise reduction from LWE to LWR unless LWE is computationally tractable. And so specifically, we show that if Q is a prime polynomial, if P is greater than Q to the 2/3, and M is a polynomial in N, and if Chi is any LWE error distribution, then any pointwise reduction from LWE to LWR admits an efficient solver that can be used to just directly solve LWE. So some remarks are in order. First of all, our result certainly doesn't suggest that LWR is easy in this parameter regime, just that it can't be reduced from LWE in this non-aborting pointwise manner. And so this begs the question of, well, what about an aborting pointwise reduction? What about a pointwise reduction that can reject some of the input samples? So prior work actually showed that LWE with uniform errors reduces to LWR in this parameter setting. We conjecture that if because the analysis of their reduction is very specific to the uniform distribution, we actually conjecture that if you change that to a non-uniform distribution like discrete Gaussians, then actually our result still holds, that you actually can't reduce LWE to LWR pointwise. And finally, we had a few parameter restrictions in our hypothesis. The first is that Q is prime. This is because we're doing a lot of linear algebra over the field Z sub Q. And secondly, we had this restriction of P greater than Q to the 2/3. And this is actually a very technical artifact of our proof that we can talk about a little later. So the main ideas of our proof is that any pointwise reduction function f from LWE to LWR must have some very specific algebraic and combinatorial structure that can be exploited to actually just directly solve learning with errors. And so what I'm going to do is just introduce a few components of this structure to you. And so the first thing I want to talk about is what we defined the correctness of a reduction function. And so what we mean by that is if you for any LWE secret vector S, if you choose some LWE input samples and you map them pointwise, you should get LWR S prime samples for some LWR secret vector S prime. So to see why this is true, what we're going to do is we're going to use what we call a pathological LWR solver argument. So we're going to construct a pathological LWR solver that's going to be a valid LWR solver. But when instantiated in our model of reduction, it's actually not going to output anything useful when given mapped LWE samples. So specifically, consider this pathological LWR sample. It's going to get as input some points, and it's going to try and find a valid LWR secret. And if it finds a secret, it's going to output it. Otherwise, it's just going to output BA. So clearly, that's a valid LWR solver. But when instantiated in our reduction, if supposing that our correctness property doesn't hold, then when given mapped LWE samples, it's just going to output bot. But by the rules of our reduction, the reduction algorithm is an efficient process that's solving LWE. And if it doesn't use any useful information from the LWR solver, then it's actually just efficiently solving LWE. And so this is a contradiction. Okay, so the second piece of structure that I want to establish on our function f is captured by our main lemma. And so under the same hypothesis, if f is a pointwise reduction from LW to LWR, then f has to have good linear agreement. So specifically, there should exist a linear map H such that with good probability over random LWE point AB, the first n components of f have to have good linear agreement with the map H. So the proof of this is very non-trivial. This is the hardest part of our paper. So I'm not going to really go super into it. But let's just assume this lemma from now and see how we can complete the proof of our main theorem using it. So just to kind of recap, what we want to show is under our hypothesis, any pointwise reduction from LW to LWR emits an efficient solver for LWE. So let's see how we can try and construct that efficient solver. Okay, so the first thing I want to do is add one more relaxation, just one simplification. And previously, I defined the notion of correctness of the reduction function to map LWE S points pointwise to LWR S prime points for some S prime. For simplicity, let's just assume that that S prime is equal to S. So what you can note is combined with our previous lemma, if I take a point, an LWE S point, AI, BI, and I map it forward under F to get AI prime, BI prime, it actually follows that AI prime is equal to HAI, and BI prime is equal to the rounding of HAI and S. And so if you just kind of rearrange that, what you get is that is equal to HAI, comma, the rounding of AI, inner product with this vector H transpose S. And so in particular, note that if I just choose a random value X from ZQ that rounds down to BI prime, I've actually guessed the inner product of this random vector AI and this vector H transpose S with probability better than guessing. So to be a little more concrete, let's construct this algorithm, this prediction algorithm pred. It takes as input a point AB. It's going to map it forward under F to obtain A prime, B prime. And it's going to check if A prime is equal to HA, it's going to output a random element that rounds down to B prime. Otherwise, it outputs something random. So you can go through a straightforward probability analysis and show that it's actually predicting this inner product with probability better than guessing, specifically with non-negligible advantage over guessing. And so what this means is you can actually use the Goldreich-Levin theorem to recover this vector H transpose S. And it actually doesn't quite work out that easily. You can't just use the Goldreich-Levin theorem as a black box because the distribution here is the LWE distribution. It's not uniform. So one of the contributions of our work is we actually proved a novel variant of the Goldreich-Levin theorem that works for the LWE distribution. One other thing to note is because here we're crucially using the fact that Q is polynomial in N because the advantage over guessing is eta over Q. And because Q is polynomial in N, this is non-negligible in N. And so the Goldreich-Levin inversion algorithm will run efficiently. Okay, so then how is the algorithm going to work? Well, first it's going to define our prediction function pred, just like we just went through. It's going to take as input some LWE pairs, and it's going to use the Goldreich-Levin inversion algorithm for the LWE distribution to recover S prime. S prime is going to be equal to H transpose S with good probability. And then we just choose a random pre-image of S prime under the linear map H transpose. And because that matrix has high rank, we'll actually obtain a guess for S with good probability. Okay, so that's just a very high level sketch of the proof of our main theorem. What I would like to do is conclude by giving a little more intuition into the proof of our main lemma. So recall that our lemma says that, okay, under our same standard hypothesis, if F is a pointwise reduction, then there exists a matrix, a linear map H that has good agreement with the first n components of F. Okay, so in order to prove this, we actually use linearity testing. So the proof proceeds in a few steps. First, what we do is we show that the structure that we can define on this function, or the structure, like the structure we can impose on this function F, actually satisfies the hypothesis of a type of affine linearity testing theorem. And then we prove a novel linearity testing result in order to complete the proof. So we do an experiment where we choose two random points, A1, B1, A2, B2, and then we take the sum of them, and we map those all forward under F to obtain A1 prime, B1 prime through A3 prime, B3 prime. And so you can show that with high probability, right, the rank of A1, A2, A3 is going to be equal to 2. And we use another type of pathological solver argument, similar to the one we went through at the beginning for the correctness of the function, to show that these AI prime values can't have full rank. And so intuitively, what's going on here is f, through this pathological solver argument, we can see that f is actually doing this, has this dimension preserving behavior. And so what this allows us to prove is that with good probability, A3 prime is going to be in the span of A1 prime, A2 prime. And so the second part of this is to prove a linearity testing result, which says that, okay, well, if that hypothesis is true with high probability, then there exists a linear map that has good agreement with the first n components of f. So the proof is very non-trivial. It uses techniques that we borrow from this classical result in algebraic geometry called the fundamental theorem of projective geometry. And intuitively, what this is doing is saying, like, okay, well, if you have a function that maps lines to lines and planes to planes, then you can exploit that in order to compute like a linear transformation that has has good agreement with the function, with the mapping f. Okay, and the third thing we have to do is we just have to switch from the uniform distribution back to the LWE distribution. We use a known result that the inner product mod Q admits a strong two-source extractor. It's a well-known result from pseudorandomness. And so this allows us to conclude that, okay, well, if this linear agreement property holds for the uniform distribution, then with high probability over an LWE secret, the same property will hold where the distribution is from the LWES. So, okay, in summary, learning with rounding is this de-randomized version of learning with errors from which we can construct PRFs. Prior work showed that LWE reduces to LWR in certain suboptimal parameter regimes. And what we show is that, okay, well, for polynomial Q, for a general polynomial M, when P is greater than Q to the 2/3, Q is prime, and for any error distribution chi, assuming that LWE is hard, the original rounding reduction doesn't work. And more generally, you actually can't reduce LW to LWR in any sort of non-aborting pointwise manner. So consequently, any reduction from LW to LWR either can't operate pointwise or must use rejection sampling. And in the course of our main theorem, we additionally proved a novel high-dimensional quasi-affine linearity test and a variant of the Goldreich-Levin theorem for the LWE distribution. And so I just want to conclude with some open problems in this space. The first is the obvious one of removing these restrictions of Q prime and P greater than Q to the 2/3. And also considering aborting pointwise reductions with discrete Gaussian errors. So we conjecture these can exist, but we weren't able to exactly prove that. Also, since we established a lower bound for proving the hardness of LWR with LWE, we think LWR is still hard in this setting. So can we find a non-pointwise reduction from LWE to LWR in this parameter regime? And then finally, one thing we didn't consider in our work is different algebraic structured versions of LWE and LWR. So one question to ask is like, okay, well, what can be said about the hardness of ring LWE versus ring LWR in this setting? So thank you very much. And if there are any questions, I'd like to take them.
We have a few minutes for questions. I'll get started. So can you say a few words, the restriction that P, the target modulus, be at least Q to the 2/3, I think it was. This is very interesting. Can you say how that arises in the proof? And do you think, is there any hope of a pointwise non-rejecting reduction when P equals 2, for example? That's like a very common choice.
Yes, yeah, okay, so first, the restriction of P greater than Q to the 2/3 was kind of a little annoying detail. That was an artifact of our proof, so it was in the main lemma. The pathological solver argument that essentially allows us to conclude that, like, maybe I'll go back a few slides, essentially like the A1 prime through A3 prime vectors can't have full rank. How we actually show this is we define a map on the LWE secrets to LWR secrets. And we show that using this type of argument that that mapping can't be many to one. And we proceed by contradiction. So essentially what we do is if it could be, then we show that like if this property doesn't hold, we show that like the ratio of LWE secrets to LWR secret, like the ratio of LWE secrets that map to these valid points versus the number of LWR secrets that produce these points is going to be greater than 1. And that sort of argument, at one point we get like a P over Q to the 2/3 thing, which is, is greater, has to be greater than 1 for a contradiction. So that's where that kind of detail comes from. I do think it can be removed, but we just couldn't figure out how to do that. And then, sorry, what was the second question? Is
there any hope of an actual positive reduction for P equals 2 or some very, very small number like that?
Yeah. So, it really, I think not. Like, I think that it won't work in that case. But so, many of that was the only place in the proof where what I just described, where we ran into this sort of restriction on, P has to be lower bounded by function of Q. So, all of the other stuff all the other structure that we imposed on the reduction function F still goes through in that case. So I don't think that a pointwise reduction, a non-aborting pointwise reduction would work in that case. But, certainly I think it's something that merits like more future study. So.
Any other question? Okay, so we'll stop there. Thank you, Parker, again.
Thank you.
And we have a track switch break, so we will resume here in 8 minutes at 14:55.